Good morning, everyone, or afternoon if you're watching this in the afternoon. Today I'm going to go through a lecture looking at the Universal Law of Gravitation, and we'll do some practice problems during this lecture for how to use that equation to solve for various unknowns related to either like the mass of the Earth or maybe the acceleration due to gravity on the moon. You can pause the video when you need to practice those questions on your own, but I pretty much just run through them as example problems. There's a set of questions also posted today that you can try that apply the Universal Law of Gravitation, and I'll post the solutions to those on the next day. Have a great day. Good to see you all on Monday and Tuesday this week, and I hope you all have a great rest of your week.
All right, so one of the things that came up last week was that if we have, let's say, our nice Earth, and we're considering the motion of the moon orbiting around that Earth. Now, we started to look at the Universal Law of Gravitation last week because the moon's orbit is roughly circular here. And what Newton realized many, many years ago was that what accounts for the moon's orbit is the same thing that accounts for the fact that all objects fall towards Earth's surface, and not just fall, but accelerate towards Earth's surface. That means that the force that causes this circular motion, this centripetal force, is a gravitational force. So there is this force that is pulling the moon inwards at every point along its path of orbit. And that's the same for the Earth around the sun and all of these celestial bodies that we see up in the night sky. Now, one thing that is worth pointing out is that for every action, there's an equal and opposite reaction. So if the moon is being attracted to the Earth by this gravitational force, then the Earth is also being attracted to the moon. The gravitational force, it turns out, is very, very similar to our electrostatic force, where like an opposite charge and a positive charge and a negative charge will attract each other. One of the kind of most bizarre things that we've noticed in the world is that masses, anything that has mass, will attract other objects that have mass. So everything around you that has mass, which is really everything, that has matter, including air, etc., has a gravitational force that's attracting it to everything else. So today we're going to examine this a little bit more. And I'm going to introduce to you the full equation for the Universal Law of Gravitation. Now I'm going to fill this out kind of as we go through this. So the universal law of gravitation is that any two masses, m1 and m2, exert an attractive gravitational force on each other. Now, one of the key words is that this force is always attractive. It's never repulsive, unlike the electrostatic force, where if you have two like charges, like two negatives, they'll repel each other. And so this gravitational force, which we can use either a little subscript of a lowercase g or an uppercase g. Here we generally see the uppercase g. Now I'm going to show you later that this gravitational force is the same as the gravitational force that we've represented before, where we're taking the mass of the object and multiplying that by 9.8 newtons per kilogram. This 9.8 newtons per kilogram is specific to Earth, related to the acceleration due to gravity on Earth. And really, this whole part of the equation that we see here reduces to 9.8 and some change when we plug in the mass of the Earth and the radius of the Earth. So that's something that we'll see. Okay, but let's break down this equation for a second. So Fg, if we want to quantify the gravitational force between any two masses, we will calculate G, which is a universal constant. So this is the same constant no matter what two masses we are considering. that universal constant is actually 6.67 times 10 to the negative 11th. And then it has all of these units, so newtons times meter squared per kilogram squared. The reason for those units is to make sure that at the end of the day, we're left with newtons so that we're in the correct units for a force. So G, same value no matter what masses we're considering. Then we take the mass of one object, mass of the other object, multiply those together, and divide by R, which represents their separation distance, and specifically the distance between the center of the two masses. So we're looking at like the center of the moon and the center of the earth. And this is showing that due to Newton's third law, there is this equal and opposite force on both objects. They're being pulled towards each other. Now, this little note here says that it says don't confuse big G with little g. Big G is this constant. So that is the universal gravitational constant. Little g is, sometimes you'll see this equation for the gravitational force on Earth, where little g is 9.8 newtons per kilogram. Here are some questions to look at this equation a little bit further and make sure we understand all the parts. It says what two factors affect the magnitude of the gravitational force? Well, I would actually say there's three factors because these are two different masses. So we have the mass of object 1, the mass of object 2, and their separation distance. And you saw that in the interactive simulation, if you played around with that last week, that you can change the mass, it changes the force. You can change this distance, also changes the force. Second question is which factor has a greater effect on the total force of gravity? Well, if we're considering mass of object 1 and mass of object 2 as being two separate variables that we can control, then the factor that has a greater effect would really be this separation distance here. And the reason for that is because you'll notice in the equation it's squared. So anytime we just change the separation distance by like a factor of 2, it would actually reduce the force by a factor of 1/4. So separation distance has a greater effect. All right, now we're gonna go through a series of calculations. We'll simplify them a little bit and then make sense of what this equation basically looks like if we graph the gravitational force versus the separation distance. So we're going to actually first draw a diagram of what is happening here. So it says you're standing on Earth's surface, and we want to just sketch what's the R in this case. So if we have our lovely planet Earth right here, there's the center of that Earth. Here you are standing in the great state of Washington. And if we are looking at R in this case, our R must be the separation distance between those two center of masses. So R in this case is going to be from center of your mass to the center of the Earth. So this would be R. Since the distance between the surface of the Earth and to its center is much, much larger than the distance from the surface of the Earth to, say, your center of mass, we are going to neglect any of the distance that goes from the surface of the Earth to your center of mass. Really, all of this distance is really just the radius of the Earth here. So we can say that R is equal to the 6.38 times 10 to the 6 meters. Now, I believe that they figured out what is the distance to the center of the Earth just through geometry and using the sun and shadows to figure out the curvature of the Earth, and then from the curvature, kind of figuring out what would be the distance from the surface to the center, what's the radius of that sphere. Okay, so we're going to calculate the magnitude of the gravitational force using this. So we just have Fg is equal to And I'll just write out the equation first. G m1 times m2 over r squared. And then G, we're going to put in 6.67 times 10 to the negative 11th. Mass of the first object, let's say that's the mass of Earth. Now, I have a little reference table that I will post on Schoology for you. It actually gives you the masses of many different astronomical bodies. So here, this part of the table is looking at satellites. So really we're looking at the moon there. So if we go down and we see here is the mass of the Earth. So this is in kilograms, so that's the correct units for us. And then we will change this radius if we get it off this table from kilometers to meters. All right, but this is the value we need for the mass of the Earth. We'll get into later how they actually calculated that. Okay, so 5.97 times 10 to the 24th kilograms. Let's say your mass is 50 kilograms. We'll be consistent there. And then all divided by the separation distance, which is the 6 point. You know what? This says 6.38, but this came up before, that this is actually 6.37. That's an old. All of these should be 6.37. Okay, and then we have to remember to square the radius. From there, big calculation. And remember that with these big calculations, just like when we were working with the electrostatic equation and Coulomb's law, the trick is parentheses. So anytime we're going to divide, we need to make sure we put parentheses and then the squared outside. So I'll show that for this one, and then otherwise, I'll let you do calculations on your own. So I've gotten in my gravitational constant. Then I'm going to multiply by the mass of the Earth. Then mass of me, and then I'm going to do the division here and then put parentheses and 6.3, it should be 7 times 10 to the 6th, close the parentheses, and then raise that to the second power. Okay, so gravitational force between myself and the Earth is 490.67 newtons. So here is where all the units cancel out. We have newtons times meters squared over kilograms squared here. The kilogram squared cancels out when you cancel the 2 kilograms that are essentially in the numerator. And those kilograms squared are in the denominator. And then the meter squared cancels out when this is squared, the radius on the bottom. All right, so there is the gravitational force on a 50 kilogram person on the Earth's surface. Okay, now we're going to move into space. And looks like we're going to do a bunch of calculations, but we're going to simplify this a little bit. So now we're going to go into space, one additional radius of the Earth above the Earth's surface. So now the Earth is still here, but now I am in orbit around the Earth. So 1r was right there, and then 2r is right here. So this is now 2 radius of the Earth in terms of the distance between, I'm going to say RE there. So now r is equal to 2RE, 2 radius of the Earth, because I've doubled the distance between myself and the center of the Earth. Okay, so to simplify this, here's what we're going to do. What's happening in this equation is I'm going to put in, this is fine. So G times M1 times M2, those haven't changed, divided by R squared. Now our R is 2 radius of the Earth squared. So if I want to simplify this real quick, I'm going to square the whole denominator. And this would now be g times m1 times m2 over 4 times the radius of the Earth. I'm going to pull out this 1/4 factor because you can see everything here is basically getting divided by 4. So this is really 1/4, forgot the squared there, 1/4 times g m1 m2 all over radius of the Earth squared, which this whole calculation, g m1 m2 over radius of the Earth squared, that is exactly what we just plugged in here. G m1 m2 radius of the Earth squared. So all we need to do for this one is we're going to divide the value that we got in the first calculation by 4. And we'll have a new, I'm going to call this one FG1, this one FG2, a new gravitational force when we've doubled our separation distance of 122.67 newtons.